this particular review question is on Fourier series. So my aim in this presentation is to work through this question step by step. It's quite a long question, but also my aim is to just remind you of some of the basic elements of Fourier series. So we've got a function here, f of x. It's defined in this way, a sort of a piecewise definition on the interval from x equals 0 to x equals 2. We're asked to do a few things. We're asked to sketch the function represented by the half-range Fourier sine series and the half-range Fourier cosine series on the interval -6 to 6. We're also asked to calculate the Fourier sine series for this function. And then using that series, at a particular point, you're asked to come up with the exact value of this infinite sum of constants. So we're going to work through this step by step. Now, just to remind you, a Fourier series is a special series that involves cosines and sines. And the way you calculate a Fourier series is you calculate these coefficients, the a sub naughts, the a sub n's, and the b sub n's. And you calculate those three parts through integration. Now you can see here that these integral formulae are on a symmetric interval, -L to +L. Sometimes when we have odd or even functions, f of x, those integrals simplify. Okay, well, let's have a look at the first part. I'm actually going to do two sketches for this, this part. First, I'm going to sketch the odd periodic extension of f, and then I'm going to sketch the graph of its Fourier series. Okay? You don't have to do that. You can go straight to the second sketch if you want to, but my aim here is to try to explain what's going on as well as doing the questions. Okay, so okay, f sub o, I'm going to call the odd periodic extension. Now, if I just draw a little sketch of the function f of x, the way it's defined up top, it's the x function on this interval, and then it jumps down to 0. Okay? So, what I want to do is, first of all, take that graph and make it, say, odd. Now remember, an odd function is just a function whose graph, when you rotate it 180 degrees, gives you the graph that you started with. Okay, so there is some, like an algebraic representation for defining an odd function, but look at this graph here. If you take this graph, you rotate it 180 degrees around the origin, you get the same graph that you started with. So that's an odd function. So for this one, what we would do is we would extend this line further down here and have this sort of in the same spot, but just on the left-hand side of the horizontal axis. Okay, so let's take our function. What we want to do now is take this function, rotate it 180 degrees, I guess, and sketch in the graph such that the rotated graph will be the graph that you started with. So what I would do is extend this down here, and this is just going to come over here. Okay? So that's certainly an odd function now, but what we want to do is also make it periodic with period 4. So to make it periodic, what you do is you take the existing graph, copy it, move it 4 units and paste. Copy it, move it 4 units and paste. Okay? So if I do that, I'll get something like the following. Okay? If I copy this, move it 4 units and paste, then I get the following. Okay, so let me just put in the markers here. Okay, now the question actually doesn't ask for that, but I find it instructive to make a quick sketch of the odd periodic extension, because from that graph we can easily sketch the half-range Fourier sine series. Okay, now to sketch the half-range Fourier sine series, essentially you can use Fourier's theorem, which says that if f is continuous at some point, then the value of the Fourier series and the function are the same. Whereas f has a jump discontinuity at the point, then the Fourier series is the average of these two limits. Okay? So what I'm going to do is go, okay, well, where are the jump points? Well, -5, -3, 1, 3, and 5. Okay? Now, essentially, the graph's going to be the same except at these jump points where the value of the Fourier series is just going to be the average of the left-hand limit and the right-hand limit. So let me show you what I mean. So what I'm going to do is sketch in the curve, but I'm just going to keep it with all open interval, open sort of dots where there are jumps. Okay, so now all we really need to do is go and look at the jump points and then work out what the average of the two limits is going to be. Well, let's just take a typical example. Let's look at this point here. This is the point x equals 1. As we approach x from the left, you can see up here the graph is approaching 1. As we approach x from the right, the graph is approaching 0. So what's the average of 1 and 0? 1/2. So at that point, x equals 1, Fourier's theorem tells us that it should be that value. And similarly with the other points, you get -1/2 there. -1/2. Okay, 1/2. -1/2. Okay, now you could, if you wanted to, go straight to the second sketch, but I actually find it instructive to sketch the odd periodic extension first and then do it. Okay, so in the top graph, this is where we are graphing f sub o, and here we're graphing its Fourier series, S of f sub o. Okay, and if you wanted to, you could label the points, etc. Okay, what about the next part of the question? Sketch on the interval -6 to 6 the the function represented by the half-range Fourier cosine series for f. So what I'm going to do in this part, very similarly, the only change I'm going to make is that instead of forming an odd periodic extension, I'm going to make it even, an even periodic extension. Now remember, with even functions, what you want this line of symmetry in the y-axis. Okay, sort of a reflection here. Okay, again, there is a way of defining it algebraically, but usually our pictures are just as good in my opinion. Okay, so let's see if we can sketch the even periodic extension and call it, say, f sub e. Okay, so we start with this sketch. What we want to do is reflect everything in the vertical y-axis. Okay, so what we would do, we would come down here and then go back up, and this would just sort of be the same along the axis, from -1 to -2. Okay, so right, so I guess that's what we're starting with. And now what we want to do is make it periodic. Okay, so you copy that, you paste it. Now, technically speaking, I probably should have one like that circle open, but it doesn't matter because this is going to sort of fill in that anyway. Okay, so it doesn't change anything. So take this, copy it, move it 4 units and paste it. Copy it, move it 4 units and paste it. Okay, copy it, move it 4 units and paste it. Okay, so now what we want to do is sketch, so this is f sub e. It's the even periodic extension. Okay, so now all we want to do is basically draw the same graph, but just look at the jump discontinuity points, right? And we might have to just place a few dots in some strategic places. Essentially just the average of the left-hand limit and the right-hand limit. So let's just choose a typical point, say 1. The right-hand limit's 0, the left-hand limit's +1. The average of these two values is a half. So what you would do is just draw the same graph with just open sort of ends, and you would have a dot there, 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 a dot there. So let's do that. Okay, that's going to be a closed one on the end. Oh, that should be open. Okay, so it'll be there, 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 there. Okay, so it's a half. So this then is the Fourier, the graph of the Fourier series. Okay, so I spent a fair bit of time on that. I'm sure you can do it faster. You may be able to go to the second curve straight away. If you can, that's great. I encourage you to do that. All right, so let's move on to calculating the Fourier sine series for f of x. Now, in this case, we want to use, I guess, part I, in the sense that we're trying to represent an odd function, an odd periodic function, in terms of a series involving sines. Now, if that's the case, we know a lot of simplification occurs. And in particular, if we have an odd function, then the a sub n's are all 0, the a sub naught 0, and we can calculate the b sub n's from this to form this Fourier sine series. Okay, now for our particular examples, the period is period 4. The big L in all our calculations is half the period. So in the formula that I just showed you, the big L will be 2. So let's see if we can knock over part 3. So if I was doing this question, I would identify that f's odd. So the a sub naughts are all 0, the a sub n's are all 0. The reason why this is true is basically because in the integrals the areas all cancel. And the b sub n's written in this general form, and I've just moved to the big L equals 2 over here. So now I need to do a little bit of calculations. You can see f of x is just x on this interval, and it's 0 on the interval from 1 to 2. So if I split this integral up into 0 to 1, 1 to 2, the second integral is going to contribute exactly 0. So really all I need to do is integrate from 0 to 1 in this case. Where the function is x. Okay? So now we reach a stage where we do need to do some integration. Integration by parts in this case. So I'm going to let x be u and sine be v prime or v dash. From those two things, we can formulate the two other functions that we use in our integration by parts formula. So if u's x, u prime is just 1. And to find v, what we do is we integrate sine n pi x onto with respect to x. So the sine's going to go to a minus cosine. And we just need to multiply by 2 on n, 2 on n pi. Okay? So now what we can do is apply our integration by parts formula. U times v minus the integral of the product of the two things that we just calculated. Sorry? How about I squeeze it in down here? Yep. How's that? Okay, so Okay. So now let's just sub in, and we can knock over that second integral. When I sub in x equals 1 into the first bracket, I'm going to get 0 because I've got a x out the front. The first part's going to give me something like the following. I'm going to get cos n pi on 2. And let's just integrate here. So the two minuses will become a plus. Cosine will go to a sine. And I just need to touch up again by multiplying through by 2 on n pi. So I'm going to get something like this. Okay, so now if I sub in x equals 1, x equals 0, the second term is just going to be 0. So I come up with a representation. Okay. So now what we would like to do is simplify this as much as we can. Think about the expressions cos n pi on 2 and sine n pi on 2. In other words, cos and sine of multiples of pi on 2. Well, they'll either be 0, positive 1, or negative 1. And the challenge is to find out exactly is there a pattern? Well, there is. Let me show you. Think of sine n pi on 2. Well, it's 0 when n's even, and it changes sign. It oscillates between positive 1 and negative 1 when n's odd. So one way of writing this is the following. This is n even, not neven. It's through this representation. This is n odd, not nod. Okay. What about cosine? Well, that's kind of similar. Cosine of integer multiples of pi on 2 is either 0, positive 1, or negative 1. So you can kind of break it down into two cases, where it's 0 or where it's positive or negative 1. In fact, you can come up with the following. It's 0 for n odd, and it's minus 1 to the n on 2 when n's even. Okay, so those little simplifications can help us a lot, and in fact it's going to help us when we get to the last part of this question. Okay, so we'll come back to that a little bit later. Let's write down our Fourier series. Essentially, our Fourier series is a Fourier sine series here, so we just want to write this out with our b sub n's here. Okay, we've calculated b sub n's to be this, and we can simplify a little bit more if we want to. Yes. Yep. So, let's look at the Fourier sine series for our function. Its general format is this, and we know that we've just calculated the b sub n's. We know big L equals 2 in this case, so we can just go through and write in the values. So if I was to do that, I would get the following. So I'm just going to use this representation first off. So that's my b sub n, and I'm multiplying that by sine n pi x on 2. Now, what I can do is introduce the n odd, n even type approach by splitting the sum up into two sums, and then simplifying with that boxed right-hand side where n's odd in some cases, even in others. So let me show you how we do that. Okay, so if I split those up into two sums, what I would do, I would use this as a guide. In the first sum, I would just sum over the even terms. Okay, because otherwise I'm just adding in 0, 0, 0, 0, 0, okay? You're adding in trivial things. In the second, when I expand into the second sum, I would go up here and I would just sum over the odd terms, because otherwise I'm just adding in 0, 0, 0, 0, etc. Okay? So in the first, when I expand this in the first sum, I would just sum over the even terms, just to have the non-zero sums. And in the second term, I would just sum over the odd terms. So let me show you how that's done. And I can replace this with that and this with that. So let me show you how that's done. Okay, so that's the first one. The second one, we're just going to sum over the odd terms. Okay. Now, sometimes we like to relabel at this stage. Instead of having, worrying about mixing up the odd and the even and things like this, we would just replace in the first sum n with values that are always even. So replace n with 2k, where k is an integer. K equals 1, 2, 3, etc. And in the second sum, we would replace n with odd values, right? So we replace n with 2k minus 1, which is always odd, and just sum k equals 1, 2, 3, etc. So as a last step, what we can do is in the sum n replace n, in this case we're interested in the even values, just replace n in here with 2k. And in this one, because we're only interested in the odd values, we would replace n with 2k minus 1 and just sum from k equals 1, 2, 3, etc. Now 2k minus 1 up here is going to simplify a little bit, and we'll get the following. Okay, we got there. Now, if you want to, you can put everything under the one summation sign, but I don't think it's necessary at this point. Now, the last question. The last question. I'll give you a chance to copy the rest down in a second. By considering the series that we've just calculated, the Fourier sine series, when at the point x equals 1, show that the sum of this special series is pi squared on 8. Okay? So for this, we are going to use Fourier's theorem again. And it just comes back to let's look at the odd periodic extension, right, at x equals 1. Okay? Well, we know that the value of the Fourier series at x equals 1 must equal 1/2. So what we can do is take what we've got, plug in x equals 1, and set it all equal to 1/2, and then simplify. Okay? So that's what our last step is to do. The value of the Fourier series at this jump discontinuity point is just 1/2. Okay, so let's go up to our big series up here, plug in x equals 1, we know the whole half. Okay, now look at the first sum. What if I put in x equals 1 here, my sum will involve sine of k pi. So what's sine of k pi where k is an integer? It's always 0, right? So that first sum disappears. It disappears. Okay? So if I go up here and plug in x equals 1, this term disappears. So it's just the other term. If I plug that in, I'm going to get a sine of odd multiples of pi on 2. Oh, sorry, that's just 1 there. Okay. Now, sine of odd multiples of pi on 2. Well, that just oscillates between -1 and +1. Okay, so if I want to simplify that, I can using the following. Pi on 2. It's -1 to the k minus 1. Okay? So now what this means is, let's take this pi squared to the other side, take this 4 to the other side. What do I get? Pi squared on 8 and what's the top bit going to be? It's a square, so it'll just be +1 in this case. That is the series here. Excellent.